Hello everyone, my name is Jang-ung Park and our class is about freeform electronics. Today we will learn about stretchable electronics first. Nowadays the electronics has been advanced very significantly, so the performance of electronic devices becomes super. And also the structure of electronic devices becomes deformable as well. For example, rollable displays or foldable smartphones and so on. So by deforming that kind of structure of the devices, electronic devices can be integrated everywhere. For example, car bodies or the buildings or even inside our bodies as well. That kind of freeform electronics can be categorized into two different groups. The first group is stretchable electronics and the second group is printed electronics. For the stretchable electronics, by stretching those device geometries, the electronic devices can be attached onto non-planar surfaces of arbitrary objects. So we can form the devices near the surface region of the object in this way. The second group is printed electronics. So we can print electronic devices as well as the three-dimensional object as well. In that case, electronic devices can be embedded inside three-dimensional object. So today we will learn about stretchable electronic devices first. In order to compose these electronic devices, we need various electronic materials, including organics and inorganics as well. But typically, most inorganic materials, such as metals or ceramics, can be fractured against the strain of just 1%. So the inorganic materials are very weak against stretchings. So let's see how we can calculate that strain. So first, let's consider the bending motions. In that case, if we bend the electronic devices, then bending-induced strain becomes applied. In the slide, you will see the blue colored region. That's the cross-sectional image of the plastic film. And if the optoelectronic devices, for example, displays, are attached onto the bottom side of that blue plastics, and then if we bend that devices, then strain becomes applied to the electronic devices. I mean the surface region, bottom surface region of the blue plastics. In that case, the bending-induced strain can be calculated by this equation. So here, epsilon is the strain, and T is the total thickness, and R is the bending radius. So here, total thickness can be calculated by the sum of the thickness of the plastic film plus the thickness of the optoelectronic devices. Typically, OLED displays has a thickness below just 1 micrometer, but the plastic film thickness is much thicker than the electronic devices. So in that case, total thickness T can be estimated by just film thickness. So here, the bending-induced strain becomes higher than 1%. In that case, the inorganic materials to compose those electronic devices can be fractured, for example. So in this way, you can estimate the maximum bending radius. So let's see the stress-strain curve of the materials. That's, this stress-strain curve in this slide shows the typical behavior of that kind of fraction motion of the materials. And as the applied strain increases, the strain becomes also linearly increases. So that's the elastic motion. So in that case, if the applied strain becomes released to 0%, then the applied stress becomes also released as well. So stress becomes 0 in that case. So the materials can be recovered to the initial stages as well. So the maximum elastic limit shows that the maximum elastic strain that can be applied without fractures. If the applied strain becomes above that elastic limit, then the stress becomes saturated, so the material shows the plastic deformations. And then if the strain becomes much higher, then the materials becomes cracked. So typically, in order to make that stretchable electronic devices or deformable, the foldable electronic devices, we should consider the elastic limit of each materials. In the case of metals or glasses, those inorganic materials shows very narrow region of the elastic limit, so they are very weak against deformations. But in the case of the organic materials, such as plastics or elastomers, they shows very, very wide elastic deformation region. So their elastic limit is typically above 5%, or for the elastomers, the elastic limit can be above 30% as well. But inorganic materials shows very narrow elastic deformation region, so their elastic limit is typically smaller than 0.5%. So that's the reason why if we stretch the electronic devices, the devices can be cracked, typically inorganic materials. Then how can you make infinitely stretchable, or how can you make multiple times foldable electronic devices using the inorganic materials? In the case of this, let's consider the substrate. For the foldable devices, various substrates can be considered, including plastics and papers and very thin metal foils as well. But each of these substrate materials have their own disadvantages. But nowadays, typically, plastic films such as polyimide are used for the foldable smartphones and foldable displays as well. But in the case of the plastic film, it's not stretchable. In order to make stretchable electronic devices, we need elastomers. But in the case of the elastomer, when the elastomer film becomes stretched, the inorganic materials can be cracked, is right? So then how can you avoid that kind of cracking issues? That kind of a cracking problem can be solved by embedding rigid components inside to the elastomer film. So in this slide, the blue colored region shows the cross-section image of the elastic substrate, and you will see the gray color part. And that gray color part is a rigid components embedded inside the blue elastomer film. If we embed that kind of rigid, very tiny tiles inside that elastomer films, and then if we fabricate electronic devices on top of that kind of rigid and elastomer hybrid components, then we can avoid the cracking problem of the electronic devices. So in my slide, I will say that they are rigid, soft, hybrid substrate. So by embedding that kind of rigid components inside the elastomer films, then we can make that kind of rigid, soft, hybrid substrate. So by making that kind of rigid, soft, hybrid substrate, we can avoid the cracking issue of the optoelectronic devices. So in this slide, the schematic image shows the example of the rigid, soft, hybrid substrate. So you will see the triangular structure of the gray pattern. That's the rigid tile embedded inside the elastomer. So in this way, if we stretch that kind of a hybrid substrate, then only the soft part, only the soft elastomer part can be stretched, but the gray part, the rigid parts are remained without deformations. So let's assume that the electronic devices are located on the gray part. Then we can avoid cracking of the device components in this way. So at the bottom side of the schematic image, you will see that all the transistors becomes located onto the gray part, gray rigid part. In that case, if we stretch it, individual transistors becomes remained without deformations because they are located on the rigid tile. But the only deformed region is the interconnection part to link the individual transistors, which is just interconnection metals in that case. So in that case, we need just one unique material, which is stretchable electrode. So if we have stretchable electrodes, then we can make that kind of entirely stretchable transistor arrays. So we don't have to develop all electronic materials to compose transistors. The only one component that we need in this case is just stretchable metals. So that kind of rigid soft hybrid substrate enables that kind of very simplification for the fabrications. This schematic, this movie shows the example of the rigid soft hybrid substrate. So here, rigid tile becomes embedded inside of that elastomer substrate. Then substrate example can be folded. So in here, the folded region is just elastomer region, and the soft elastomer region becomes folded, but the rigid part becomes remained without deformations. So in this way, we can conform completely. So here, important thing is the interface between the soft region and the rigid region of the substrate. When the substrate becomes folded, the interface should not be separated. So we need really a good binding between the soft part and the rigid part of the hybrid substrate. So in this SEM image, you will see the interface between the soft part and the rigid part for the folding conditions. And that interface becomes very well contacted without separations because they make continuous conformal binding. So that's very important for complete folding issues. And another important issue here is the standoff height between the rigid part and the soft part. That kind of rigid soft hybrid substrate can be composed by the rigid epoxy with the PDMS elastomer. So by making that kind of PDMS and epoxy hybrid substrate, we can reduce the standoff height. So in this way, we can make almost flat surface regions. So as shown in these AFM images, the height difference between the rigid part and the soft part becomes below 50 nanometers. So it's almost flat. So in this way, we can do the photolithography for the device fabrications. And then by using that kind of rigid soft hybrid substrate, we can directly fabricate electronic devices. For example, transistor arrays with the active matrix forms. So in this slide, the real samples image is shown. So these samples images can be folded in sequence. So in this way, we can do the complete folding without fracturing of the materials, the transistors, for example.